So everyone, this is Andrew Youdin. He's visiting us from the University of Arizona, and today he's going to be talking about the formation of planetary or binary planetesimals. So take it away, Andrew, and I very much apologize.
Okay. So as was not said in my introduction, I'm a former citizen. I was here for 4 very good years, and so it's really a pleasure to be back. And so this topic of how planetesimals form is something I've been working on off and on basically my whole career, at least since I started working in astronomy. And so here's just I've worked with many people over the years. This is just a list of some of my most recent collaborators on the stuff I'm going to be telling you about today, including most importantly the PhD student who's working with me, Urshan Lee. He's responsible for most of the at least the recent beautiful simulations I'll be showing you. David Nesvorny at Southwest Research Institute, he's really sort of led the charge on connecting planetesimal formation theory to Kuiper belt binaries, and that is work that is very nicely coming into fruition. And then Jake Simon and Phil Armitage are also collaborators on the streaming instability work. So I mainly work from a theory perspective, and that gets involved in simulations and trying to understand how planetesimals form. And it's really exciting to get our first up-close look at sort of outer solar system planetesimals. And a reason why this is in some ways more exciting than the asteroids that we know very well is the asteroids belt is not a very pristine environment. There's been lots of collisional evolution and lots of bombardment by solar radiation. For instance, you have binaries in the asteroid belt that are just caused by rotational spin, radiation spin up and fission. But you're seeing something much more primordial when you go out to the Kuiper belt. So that's obviously a phenomenal thing the New Horizons mission has done. So just to take a step back, as discussing with some people over lunch, there is a dominant paradigm for how we think most planets in the solar system and extrasolar planets form. You can generally put things under the rubric of this core accretion model. And the first stage of this model is the one we're going to talk about most today, and that's sort of growing from small dust grains up to planetesimals, things often defined as being, there's been sort of an upward definition of the definition from 1 kilometer up to the 100 kilometer range, depending on what you think forms and how. But then those are then the building blocks of larger planets, building up terrestrial planets and the cores of gas giant planets. And then the accretion and core accretion, often people associate that most with this, if you grow the solid core big enough, quick enough, and where the gaseous component of the protoplanetary disk is still around, that core can then accrete a dense gaseous envelope, maybe undergoes some sort of runaway, and leaves you with a gas giant planet like Saturn or Jupiter. And then, of course, things are caught somewhat in between that are Uranus and Neptune-like. And then, of course, a big confusion of all this is that as planets are growing, they're, of course, interacting with other planets and also with both the solid and gas components of the disk. And this causes them to causes their orbits to change in various ways. So I know there's a lot of people who work on larger scale problems in astrophysics, and so I just like to make the argument that actually this formation of planetesimals is actually the biggest problem in astrophysics in terms of the numbers of orders of magnitude involved. And so, going from micron-sized dust up to 50-kilometer planetesimal, that's growing in mass by a factor of 10 to the 33. And this is not some simple self-similar process. There's lots of different physics involved as you go through that mass scale. And once you're at a planetesimal, you're basically all the way there. So the rest is just details. Well, it's been an exciting time. I mean, aside from the flyby, the other thing that's come out in relatively recent weeks or a month or so was the public release of this large Alma program studying some of the brightest disks at very high resolution. This is this D-sharp program studying disk structures at high angular resolution. And so it was already known from Alma still, but that all disks that are large, at least, appear to not be simple, smooth objects as you might have expected from, alpha disk theory, right? They're much more complicated than that. And that rings appear to almost be the rule. There are also spiral structures. They're a bit harder to see in the continuum. If you look at some of the other papers in this series where they do the continuum subtraction, you can see beautiful spirals in some of these objects. And you can start to see them even at this projector and resolution here. But yeah, disk structures appear to be the rule, at least in bright disks, which are also large disks. And obviously, to see them as well as possible, you want to do this at high angular resolution. So typically here, what we're getting is 0.05 arcsecond resolution, which at the characteristic distances of these objects, which actually have recently been updated by Gaia, so we know the distances a lot better. Their goal was to get 5 AU resolution, and they're getting that for these objects. These are sort of 10 AU scale bars here. So my goal is not to overview the observations in great detail, but to discuss here what do we learn about planet formation from the fact that disks are not simple objects, but are so complex. And the answer is, frankly, well, we still don't really know, right? That there's a sort of classic chicken and egg problem here. Because on the one hand, you might think, oh, these structures are what help you make planets. On the other hand, you might think, well, it's planets that are causing these structures. And it could be either or both or some combination. So one of the papers in this D-sharp series actually asked the question, if you want to explain these structures by planets that are opening gaps by their gravitational torques and make different assumptions about the disk viscosity and things like that, obviously, there's lots of assumptions you can make, so there are huge error bars on what the masses of the planets responsible for some of the most significant gaps in those observations are. And you see, for the most part, they are falling in a window that is not actually observable. That most of this parameter space is too far out to be detectable by radial velocity or transit methods. They're just not, these aren't the right kind of stars to be doing microlensing on. And they're potentially too dim for direct imaging to find them. So lower mass planets are too dim. So it is possible that there are planets there, and this is a population of planets that has not been probed by other means. But on the other hand, while that would be nice, then that means, OK, you can't necessarily appeal to these structures for how you form planets in the first place, or at least how you form the first planets in any given system in the first place. Now, the idea that these might be sites of ongoing planetesimal formation in particular has some support from the observations when the properties of the rings are studied in detail. You combine their brightness with some estimate of what you think the disk temperature is. And the conclusion, at least of the authors here, was that these are sort of marginally optically thick. They seem to be around 0.2 to 0.5. And that's sort of a special value. And the thing is, what could it be that's self-regulating the optical depth to be just below unity? And they actually made an argument that, OK, it's not definitely that, but it is feasible that there's some ongoing planetesimal formation, perhaps by something like the streaming instability, because that's something that would kick in when the amount of solids relative to gas increases, and then you form planetesimals from those small grains, and that could drop you back down to a subcritical level. So that's an argument that's been made. So however the rings got there, it is interesting to note that there was actually a prediction that maybe they had to be there just in order to explain disk lifetimes. Now, actually, I don't think I need to explain this prediction to you in great detail, because Paula told me just before I left here that she's coming here in March to give you a talk on her work. So you'll get to hear more. Although, frankly, she's so productive, she's probably going to talk about things she's done since then. But yes, it is important to note that she made this prediction that the ring structures would be observable by Alma in the nearest star-forming regions. Produced simulated images that are pretty good, and full 3 years before Alma actually found them. So a real prediction. Yeah, she predicted that too. So yeah, it's really quite impressive. So who has had the radial drift and meter size barrier explained to them a million times? Okay, few, but okay, I'll do it once more very quickly, sorry. So okay, the fact that small solids have short drift time scales, meaning drifting inward towards the star in smooth protoplanetary disks, is a sort of well-known thing. And the basic reason for that is if you look at a gas particle, gas parcel in the disk, its orbital motion is you have gravity that's it's not a purely Keplerian orbit where gravity is balancing the orbital motion, but there's also a pressure gradient in the disk that on average in a smooth disk points outward, and so that means the gas speed is a little bit slower. Now the consequence of that slower than Keplerian speed for solid particles that are orbiting in the disk depends on the size of bodies, and when thinking about aerodynamics, we describe particle size in terms of an aerodynamic stopping time, how quickly it responds to drag forces. So small particles respond quicker, so they have this small number, and it's dimensionless just because it's normalized relative to the orbital time scale. So, this stopping time being much less than 1, we're talking about a very small dust grain. In that case, it's very well coupled to the gas, so it's orbiting at the same speed as the gas. And it's just glued very quickly, so it actually drifts in very slowly. On the other hand, if you have something that's very weakly affected by the gas drag, a huge planetesimal that's already formed, it's going at a Keplerian speed, right? And so it's seeing this gas headwind, but again, the effective drag forces on it are weak, so it's being robbed of angular momentum, but very weakly, and so it's drifting in slowly. So there's a sweet spot, right, where you're in between these two regimes, or you have the headwind, but you're actually responding most strongly to the drag, and that's when objects drift in fastest. And you can sort of see here that special size, at least in standard disk models, it depends on your gas density, is somewhere around 1 meter or maybe tens of centimeters in much of the inner disk. And then as gas densities drop, and there's also different regimes and drag laws that change that we don't want to get too much into the weeds of, but that as you go towards the outer disk in the regions that are, for instance, being observed by Alma, that actually the fastest drifting solids would be in the millimeter to sort of centimeter range, which is sort of what you're actually looking at. So that's sort of the point that, okay, we know these millimeter grains are sticking around for much longer than 10 to the 5th years. The age of the systems are closer to 1 million or a few million years. So you actually need some kind of dust trap or some method of generation and regeneration to explain why disks why disks persist for so long. And then in addition to explaining the observations, you also have to want to explain how you form planets, right? If you try to grow everything in a piecewise manner and you lose it in faster than reasonable growth timescales, that's a big problem. There's a review article that I wrote a few years ago with Youdin Cheng that sort of tries to summarize the state of the art of, as of that date, of what the issues are. Things have changed a bit, but not that much. And the basic issue here is, we want to climb this size ladder of growing in size from micron to above kilometer size. And again, we can think of that in terms of these aerodynamic stopping times, which also change by many, many orders of magnitude. And the first thing that happens, that we know happens, is that dust grains grow by sticking. But then the question is, if that can't go fast enough, then in addition to this bottom-up process of collisional growth, we also think there are relevant top-down formation processes where you take a cloud of small particles and concentrate them to high densities by one mechanism or another, such as the streaming instability. And then when the densities get high enough, you can have rapid gravitational collapse into planetesimals. So the modern view is probably a blend of both bottom-up and top-down growth is relevant for forming planetesimals. So quickly, there could obviously be a separate talk on just this. There's a lot of interesting both theory and especially laboratory work on how actually does this growth by sticking work. It's a difficult process to actually model from pure thought. So they do experiments such as in drop towers to simulate the zero gravity environment. And yeah, you sort of, what you find is that there does tend to be, especially for silicates, the story gets a bit more complicated for ices, but that there's a very inefficient growth beyond even millimeter sizes, and you first get sort of a bouncing regime, and then you eventually get, as the velocities get higher and higher, into a fragmentation regime. And just to sort of set your mind for what these velocities mean, the sort of headwind speeds we were talking about due to this pressure support, that was of order sort of 50 meters per second, right? So 100 is a meter per second. So yeah, kind of in the fragmentation regime. So that's an issue, and some experiments have even been done on the space shuttle there. So in terms of how to collect solids, well, the oldest idea, which is still a good one, and what we may be seeing in these disks, is that this idea of radial inward drift, that only applies if the pressure gradient, right, is always decreasing. If you can create a pressure bump, well, then the direction of migration reverses on both sides of that pressure bump, and so you will simply collect particles in that pressure bump. Now, it turns out that a pressure bump does not have to be a perfect ring. It turns out if you have an anticyclonic vortex, which is the type that is more likely to be stable on a protoplanetary disk, that the hydrostatic and rotational balance that gives you is that these anticyclonic vortices are also pressure maxima. And so then for actually a very similar reason as the ring case, they also collect particles. And there have indeed been observations of sort of very dense clumps of dust that appear to be resembling vortices, even if the source of these vortices is not fully understood. And in many cases, these strong observed vortices tend to come in disks with a very clean gap that is probably hosting unseen planets, and then the planet may be triggering the formation of that vortex. Okay, so these are sort of large-scale ways to concentrate dust. There is also some small-scale ways to concentrate dust, and one of those is the streaming instability. And so the notion here is that instead of having some pre-existing structure, the idea is actually the particles effectively cause their own concentration. That it's the fact that you do not only have drag forces on particles, but there is a back reaction of the drag force on the gas that affects the flow of the gas that then causes the particles to clump together, similar to a bicycle peloton or a flock of birds. So just to see that in this very simple sort of 2D height versus radius simulation without vertical gravity, so things won't settle, but you'll just see particles drifting in, and the color map here is just particle density. And so you'll see that structures start to form, and the initial wavelength of that is understood analytically, but then the growth continues into a nonlinear region and gets the densities get quite high. Actually, in many cases, the peak density seems to be limited by numerical resolution. So you can easily reach over from, you're starting at a particle density that's comparable to or less than the ambient gas density. And numerically, it can reach thousands of times the gas density in the highest density peak, without any gravity included, a purely aerodynamic effect. So that's a little surprising. But there's sort of little doubt that it works because it can be derived relatively simple. From the simplest way to do it is to consider the dust or particle population as a pressureless fluid, and then you have basically standard fluid equations where you have a drag force between the two components that just obeys Newton's third law with the back reaction on the gas. And then the driver of it is simply the pressure gradient acting on the gas. Yeah.
Gas is incompressible.
For this analysis, yes, but you don't need to. It just makes it simpler. The sound waves are not, that basically just filters out the sound waves. So yeah, the simulations are fully compressible, and yeah.
Do you also need a decent amount of dust density in order to drive this?
Exactly, right. So if you were to go to sort of the test particle limit where this factor would go to 0, there would then be no back reaction on the gas. And yeah, we'll have a little bit more on that. So here we're just modeling it as a linear drag law. In some interesting recent work by Squire and Hopkins, they've considered sort of and so it turns out both Epstein and Stokes drag does apply, this linear regime applies. Things get a bit more complicated if you want to have nonlinear drag laws that are nonlinear in velocity. And Squire and Hopkins have actually considered those regimes, and the behavior changes slightly, but nothing fundamental. So yeah, so the existence of an instability is something that you can do pretty easily with Mathematica, but then studying the nonlinear evolution is a bit more involved. You need to do to do this well, you need to have a combination of a hydrodynamic simulation for your gas plus evolution of the particles. Now, recently, some people have actually, groups have tried doing the two-fluid approach numerically as well, which is quite challenging, but they actually seem to be doing it. We don't need to get into those issues now. But the basic issue is that because this is such a small scale instability, I'll be pointing out some of the scales in a little bit, you can't simulate how this happens in an entire disk. You need to choose a patch or a simulation domain. And similarly, you can't have a one-to-one representation of each particle in your simulation as corresponding to one dust particle. You have sort of a statistical representation, and so we just call them.
With a single
not in this approach, yes, but then when you're doing the simulation, you can actually give each particle a different property if you want. If you're doing it numerically with particles, it's not different fluids. It's just you're doing, and when this is done, you have a single hydro simulation, and then you have millions of particles. Now, in principle, you can give them each a different property. In practice, often simulations are done just with a single stopping time, but they've also been done with sort of a range of stopping times. Usually, it's like several bins, not an infinite range, just to keep track. But yeah. So yeah, there's always a difference between what can be done and what has been done yet. But yeah. Okay, so while the very first simulations did not include vertical gravity, that's of course unrealistic. So anything where you're trying to understand what happens in reality, you include vertical gravity as a consequence. Most of your solids, this is sort of a view of the gas of. This view happens to just be of the vertical momentum for some issue we were interested in. but the solids are all in the midplane. Now you might think, okay, this is basically a 2D system. You should be able to simulate a very thin layer. But unfortunately, this dust layer launches all sorts of waves in the gas that you can see here. So you actually have to simulate sometimes a fairly, fairly thick region of the disk, just so you don't have artificial reflections going back to the midplane that are too serious. So that is one of the things that can increase the cost. But again, you can see here in this nice visualization that one of the initial things that happens is there's primarily axisymmetric concentrations of dust, but then within those there are some very high density knots, and then it's those highest density knots that we think can go on to form planetesimals. No. So these are not. These are not. Actually, if you look at this paper, we actually address this issue in detail. There, as you go to larger boxes, you can get zonal flows, but that's not where the particles are. So it's interesting. I don't know if people had shown before this that you can actually get zonal flows without MHD. Turns out it depends. We found it depends more on the vertical boundary condition. But the point is that this concentration mechanism is quite different from the pressure trapping. It's much more dynamical. So it's not why the particles are clumping at all. And just to the more general question of, okay, is a local approximation good? It's like, as we assume it's good just because the length scales are so small. And there have been studies with different box sizes. So we don't see a significant effect on box size. So we don't think that's a big driver. I think. Okay, so this is a bit qualitative, but just meant to give you sort of an overall understanding that sort of, when the streaming instability does not always cause particles to clump to very high densities and form planetesimals, right? There have to be, the conditions have to be right. And so I just want to give you a flavor of what those conditions are. The first is simply that the disk cannot be too turbulent. And basically, you need particles to be able to settle towards the midplane. If it's too turbulent, they won't do that. Now, there's a couple sources of turbulence. Well, there's many, probably infinitely many sources of turbulence you can imagine. But we can broadly say, oh, there's just some sort of turbulence that just exists in the disk, either because of magnetic or some other effects. But then there's also the turbulence that's generated by the particle gas feedback themselves, which, as I said, is ultimately driven by the radial pressure gradients affecting the gas. So many of the simulations I'm showing you, we've sort of set, and we haven't included any external sources of turbulence. We're only doing the self-generated turbulence from the particles themselves, which is admittedly in some ways a best case scenario. Aside from the fact, as Hanno was saying, that the external turbulence may generate zonal flows that trap the particles and bring you to higher densities. So it's not, it's sort of never categorical. But yeah.
Does that plot show the regions of instability?
Yeah, it's sort of, I'll explain it. Yeah, green is go, red is don't go. But yeah, yeah.
So what's the constraint on the scale height of the?
Yeah. So the constraint is, again, that this is a feedback effect of particles on the gas, right? Generally speaking, in terms of overall abundances, you have, right, roughly only 1% or maybe less of your mass can be in dust grains, but you need to get towards a 1-to-1 ratio in your local density of particles to gas. And so obviously settling things down to the midplane is, is at least one way to start to get there. So that's why you need that. And so yeah, so that's the other thing, is you have to have enough particles. So both in terms of the global abundance of how many of them are, and obviously how well they settle to the midplane. And then if you assume it's only radial pressure gradients, you can say, okay, what's the column density ratio? What's the local surface density ratio of solids to gas? People often crudely call this a metallicity of sort of pebbles, even though it's not an astronomical metallicity. And so this is a quantity that has to, in general, be at least sort of 1%. That's what's sort of shown on this plot here as sort of the sort of minimum value it can be to be in that green region. And then the other thing that matters is, right, you can't actually do this with small grains. You have to have larger pebbles. And so the other way to say that is that this stopping time, right, can't be too small. And it probably also can't be too large, because then they're not affected by the gas. But we generally think we're more constrained by how big things grow than things growing too much. And so, yeah, there have been a couple different works. There was some earlier work suggesting that the boundary was here. And then there was some work with new numerical techniques suggesting you can get particle clumping going into even smaller and smaller particles. But the clumping gets weaker as you do this. So there's a bit of a game to play there. But those are the basic ideas of what you need to have this work create large concentrations that are relevant for planet formation. So there's so there's two schools of thought on that. One is that, oh no, you need this to get to high densities in order to get gravitational instability. That's the simple story. But then there's also a sort of, that's what you need to have rapid dynamical gravitational instability. There is a possibility of sort of slow, long time scale secular gravitational instability, which has actually been, I've worked on that a bit, and others are still working on it. And it is put out as a possible explanation for the rings observed by Alma as well. So that is something that at this stage has still only been studied analytically, and so we need a bit more numerical work, but it's very hard because it's large length scales, still needing to resolve the small ones, and long time scales. And so it's, yeah, we're working on that as a next step. So whether there's another way around. And actually, it's Urshin who's starting to do some of those simulations of and it's basically pushing into this lower stopping time regime where, okay, you don't have small scale clumping, but might you still be able to get gravity collecting the dust into larger scale rings, aided by dissipation. So, okay, so I want to show you sort of some of our most recent simulations here. These are done with the Athena code, famous hydrodynamics code with particles added. People are working on adding this particle module. Actually, Chao-Chin Yang, who made the last plot I showed you, is working on adding particles to the Athena++ code, which should make things even better. This is originally done by Juning Bai, working with Jim Stone, and then Urshin Lee added some refinements to the code, including the vertical boundary conditions. He's also written an impressive sort of clump finding algorithm that's actually based on some cosmology work in order to identify, as you'll see, these often overlapping overlapping clumps that form in the simulations. And just so you know what you're seeing here, this is a different view than the last time. The x direction here is still the radial direction, but we've now got an overhead view. So this is the orbital, the orbital plane with Keplerian shear going like this. And so what you're going to see here is, right, the streaming instability has already been operating for a while, and it's sort of formed these sort of shearing structures. And what this is now going to show is what happens when you enter the self-gravitating phase. Okay, and so you see that the sort of knots sort of start to form and grow in density. And the hills here are, these are the circles here are the size of the Hill sphere. These objects, you see you have quite a range of masses and things sort of overlapping. And this is sort of one of our goals, is to obviously understand this mass distribution and where it comes from. Well, I mean, the accretion is just being modeled numerically, and the Hill sphere is for, is sort of for, it's just sort of for edification. So I'm not saying it's responsible.
If the boundary radius is smaller, then anything that enters the Hill sphere doesn't enter the boundary radius, just.
So in this context, I'm not sure what Bondi radius means, right? The particles don't have a sound speed. Yeah, this is right. These are right. This is all particle density. I mean, the gas is there, but
If you made a histogram of the velocity, that velocity would have just something like.
sure. So yes. So sure, yeah. But again, this is not explaining. Obviously, it's not true that everything that's inside here is getting accreted. Things are moving through. So I think that's exactly your point.
So are these things self-gravitating, or is that what you're?
Yeah. So sort of. Well, yeah. So sort of by the standard definition, you can be right. The gravity is dominating the stellar tidal gravity inside this Hill sphere. Although obviously, if something has too big a velocity, it won't be bound. But in general, yes, things are. In general, the clumps are confined to well inside their Hill radii. So yeah. That's a great point. So it turns out the late times of these simulations are probably not realistic because the amount of collapse you get is inhibited by your numerical resolution. So even though this is not realistic, I want to show it to you anyway because it's kind of cool. It's maybe fun for looks like sort of galaxy formation simulations. So one of the things you can do is look at what happens when there's a perhaps artificially enhanced sort of tidal interaction between two objects. So if you look at the sort of orange and red dots, this is what happens to them in the end. So these orange and red dots, they have these close encounters, and they get sort of they can get sort of tidally stripped as they encounter. You can sort of see them coming into each other there. And then there's another cool thing that happens down here, a little galaxy merger. So those two, and that's a nice violent crash. Yeah.
Particles are either individual or are they modeled by a single velocity?
So yeah, there's no sync particles in this. So we start out with however many 10 million particles we start with, and then they just stay as particles. But they're not, right, because the gravity is done, partly because the gravity is done in an FFT way, they're never really collapsing beyond the gas grid cell size. All right, so what is, what's sort of new? There's actually lots of different directions people are going with this type of work on talking about the streaming instability and how it interacts with related mechanisms. So one thing that I already pointed to is that there's even though it's simple to do the analysis and write it down, it's a little harder to understand exactly why. It's like there's not unlike the MRI, there's not a simple sort of spring analogy. I mean, you can kind of say it's like a traffic jam or it's like a bird peloton, but that doesn't actually explain the physics in great detail. So Emmanuel Jacquet, speaking of former citizens, when he was here, he actually did some work on this, or maybe he did this before he got here, I don't know. But anyway, sort of extended some of the things in the original paper with Jeremy Goodman as sort of looking things in terms of geostrophic balance and whatnot. And again, those are approximate, get you part of the way there. Min-Kai Lin, some you all may know as well. When he was at Arizona, he actually looked in general at sort of drag-driven instabilities and sort of showed how you can sort of explain the existence of these instabilities and sort of PDV work done done during an oscillation. I sort of hid the fact that these are not actually instabilities, they're overstabilities, so you have a cycle that grows. And basically that explanation actually explains why, as I was telling Hanno, that you actually don't concentrate these particles in a pressure maximum like in the static case, but there's always a phase difference, and he explained why it's a phase lag, not a phase lead, so some extra things we're understanding. And then Squire and Hopkins, there's actually a series of papers, and at least one of them, Hopkins is the lead author, but where they are sort of showing that there's actually a whole class of drag instabilities, of which the streaming instability is just a special case. And they've added magnetohydrodynamic effects and things that could be relevant in sort of stellar wind outflows. So a lot of so a lot of exciting generalizations there. Now, another issue is that, okay, as we said, there are these local, effectively very local conditions for triggering this small-scale instability. But then the question is, well, when does that actually get triggered in a realistic global disk model where particles are growing and coagulating and drifting, and can you actually get it to happen? And it can be a challenge, and so people are working on how to make that happen. Another huge effort that Jake Simon and Phil and I and others have been involved in is trying to understand, what is the size and mass distribution, that you get. Because this is ultimately, if you think this is actually how planetesimals form, you want to compare these distributions to the solar system, see if you're getting a good match. Now, of course, things don't necessarily stay like this. They can grow some after that, so you need to understand that when you're making your comparison. But generally what we find, and this is at least qualitatively similar with, for instance, the Kuiper belt, is that there's a mass range where you have a sort of fairly flat distributions. These are cumulative mass distributions, so number above a given mass versus mass. There's sort of different units here. This is total mass in the box, which is purely a numerical thing, whereas this is standard gravitational mass, just defined by the Toomre wavelength of the particle surface density in the disk. And so in all cases, there's sort of a similar behavior where there's a sort of flattish slope, maybe going as mass to the minus 0.6 or something like that, that then steepens at the high mass end. And so in this study, the goal is to study different stopping times and see how that affected, how that affected the size distribution. Now there's how it affects the shape, and then there's also how it affects the overall efficiency of formation and how much stuff you make. And then in this study below, the effect here is varying the strength of the pressure gradient. So that's all this parameter is here. It's just the way we chose to measure the strength of the pressure gradient. And so clearly, as you increase the pressure gradient and the headwind speed, you get less and less efficient formation and often form a bit smaller objects at your biggest size range. But the basic gravitational scale is still something that's it's giving us, giving us at least the order of magnitude of the scale that's relevant here is just from the simplest physics you can imagine, just gravity plus the disk rotation rate. Okay, and so, but what I'd like to focus on in the remaining time is actually what we're looking at also, not just the masses of these clumps, but how they're rotating. Because again, we're not able to model the collapse all the way to a solid object, but we think if there's if there's a lot of rotation in this clump, you won't be able to just put all that mass into a single object. You have to either get rid of the angular momentum, well, you have to get rid of the angular momentum somehow, and forming a binary is one way to do that. So now let's take a step to the side and go back to the what we actually see when we go out to the Kuiper belt, or what we saw before New Horizons got there. So it was known that there was a very high binary fraction in the Kuiper belt, and that's especially true for cold Kuiper belt objects. You might say, aren't all Kuiper belt objects cold? No, I mean dynamically cold, meaning low eccentricities and low inclinations below about 5. And so it's this population that has a binary fraction that's at least 30%, because the binary fraction is limited by your angular resolution from HST and ground-based telescopes. And so in practice, that means you're looking at separations that are bigger, in many cases much bigger than 1,000 kilometers, right? So definitely nowhere near the contact binary of Mu69 that's only 10 kilometers apart, right? We're not getting anywhere near the contact binaries, even with HST. And the other thing is that these are mostly equal mass or relatively equal flux, not perfectly equal, but again, that's sort of an observational limitation, but it actually does seem to be that that's what's quite common. You do seem to be forming in quite significant numbers, relatively equal size objects. And the general scale you should be thinking about here is sort of order 50 kilometers. So this is not Pluto we're talking about. These are much, Pluto Charon, these are much smaller binaries. Okay, so what's shown here is one of this earliest evidence that it is in this cold population, right? That if you look at the objects in the the objects that are binaries, right? They tend to all have these relatively low inclinations, whereas the non-binary population has a much broader inclination distribution. And so the simple interpretation of that is that whatever caused these things to get high inclinations and scattered them, that also destroyed the binaries.
Do the binaries also have low eccentricities, the ones that have these low inclinations?
So in general, yeah. So that's in some ways, that's sort of a definition of what this cold classical population is you can put a cut on and the idea that these cuts aren't just arbitrary is that when you do that dynamical cut, you also get a difference in the average colors of those populations. So they do seem distinct.
And so then that must mean that they form really early. So what circularizes these binaries? Do people have any idea?
Oh, what's it? Yeah. So sorry, what do you mean by, yeah, so.
So I mean, if they are formed through a three-body encounter, I'd expect that they would have a high eccentricity. But if they're formed really early on through
So yeah, all right. So I'm going to get to this. Several of those. Yeah, there's a lot of issues there. I'm going to get to some of them later. But I think the main thing to be clear on now is that here, the inclination that I'm talking about is right, because these are single objects and binaries. So these are the inclination of their orbit around the sun, not the orientation of the binary. Right, so we'll get to the orientation of the binary in a little bit. But for now, this is just talking about, right, you see something, you don't know if it's a binary or not. You characterize its orbit as a single object, and that's the inclination that's being plotted here. Yeah, so it's another Canadian, actually, Wes Fraser. So there's been a growing consensus, and this is the paper that just put it out sort of recently and most bluntly, but there's been this growing consensus that essentially all planetesimals born in the Kuiper belt formed as binaries. And so there's I said, oh, the observed fraction was only 30%. How do you go from 30 to 100? Well, first of all, you can say, well, 30 is close enough to 100. You can also say that, well, even though that, so several things. There's also like, oh, that 30% only applies to this special population. So you can say, how do we know that special population is representative of what happens in general? And that's that, right, this cold belt, right, it's not that the eccentricities around the sun, it's like this is the most dynamically unperturbed population of planetesimals that we know about, right? It's both dynamically unperturbed, right? They never suffered strong interactions with Neptune or any other planet. Even Planet 9, if it exists, is too far away to do much. So since it's the most foreseen, it should thus tell you about what happens sort of in general. The fact that you can get from 30% to 100%, some of that's as well, you're just limited in what the separations you can see from the ground. And then well, this was not included in this paper because it happened yet, but now we have the additional knowledge of the flyby of MU69, which was not selected for being a contact binary, selected because it was the only thing they could find on the way out of the solar system. And lo and behold, it's a binary. And then this particular paper had some details that was based on these detailed sort of color arguments that, oh, they found something that was in this scattered population, but then there was some binaries among the least scattered members of that scattered population that sort of, further pointed in this direction that it's this universal process. But you also asked, oh, you think they formed by capture? Well, how did they form? That's what I want to ask you about. But I guess before asking that, I would say they're still being too cautious. I'd say, okay, there's also nothing special about the Kuiper belt that actually all planetesimals formed as binaries, because why should the ones that formed in the Kuiper belt be any different than those that formed anywhere else? We're just seeing seeing a particularly well-preserved population. Okay, so one huge clue for trying to understand how these form. So I said, oh, okay, there's often some general trends in color. Okay, this is not a general trend. This is when you look at the primary and secondary components in a binary pair. Within the errors, the colors match essentially perfectly, right? And this is, right, and this is obviously, and so this is just R minus I colors from Hubble for, right, for the set of objects that was known at the time. And so what you can see from this is that even though the primary and secondary match quite well, there's an overall color diversity, right? So, color is representative in some way of composition, at least the surface composition. So same color, you can assume it's the same stuff, at least on the outside. And so Ultima Thule, the colors of those two lobes are also the same, sort of suggesting that, okay, the contact binaries, there's nothing different about them aside from being much closer in a contact binary than these more widely separated binaries. Now, there's no simple way to explain how you make the two components the same if they were not originally the same. There's no obvious trend here or way to explain it easily in terms of heliocentric distance, either average distance or pericenter distance. And especially for things that are widely separated, there's no way to resurface and get debris from one to the other and make the surfaces the same color if they weren't originally the same color. So it seems pretty hard to get around that one way or another, each pair formed from the same stuff, even though the stuff that was around it, either at that time or at a somewhat later time, the stuff had changed. Okay. The simplest way to form things from the same stuff is just to say they formed from the same stuff, to this mechanism that I've told you about already, that you form a dense cloud of pebbles or other particles, and then when that collapses, it doesn't collapse to a single object, but because there's some spin and angular momentum, that excess angular momentum goes into creating multiple objects, and which is definitely not limited, at least initially, to binaries, although if you form more than two, you're much more likely to go unstable and dynamically unstable and wind up with two. Okay, so obviously doing it this way, it explains the matching colors. There's also some very wide binaries that are hard to explain by these other capture mechanisms that I'll discuss. And so the question of whether we can test if they form by this way or another way is to ask this question now about what is the inclination of the binary itself. What's its actual orientation? Did it form in the disk, rotating prograde, retrograde, at tilts of angles? Turns out that's difficult to do. You have to characterize this binary orbit very well. There's usually two degenerate solutions. It takes a lot of work to undo that degeneracy. Will Grundy and others at Lowell Observatory have done this work. So what we did, though, is we went back to our simulation where we found all these, self-gravitating clumps, and then we looked at the rotational properties of these clumps. And so we actually looked at was angular momentum. This is vorticity, which is different, but it's just for visualization. And you definitely can see that there's a preference of strong prograde sense of vorticity and rotation in the in the dense clumps, right? And so what you can do for several different simulations, the details of the differences here don't matter. You find that there's a broad range of these obliquity inclinations, but that there's definitely a strong favoring for prograde. That there's sort of 75% or so are in the prograde direction. Yeah.
So is the only turbulence from the streaming instability in the simulations?
Yes. Yeah. So you can ask how you might. Maybe things would get more isotropic, or maybe that turbulence would also have a, it might also be sheared out and favor prograde.
Are there directions apart from the plane rotational direction? How does this include all directions? Is there a strong preference for being prograde and retrograde that align with the background rotation
I'm not sure exactly what you're asking. So the sense of the disk is defining what prograde is.
Right. But when you're so you go, there are prograde ones, there are retrograde ones, but how about?
Yeah, no, that's what this angle is where you are. Yeah. Sorry, this maybe you can't, 0 to 180, so all possibilities. Yeah. Ignoring ascending node and other things. Yeah. So these are different simulations. Now if we compare the simulations in solid to the observed distribution. Now, so again, this is sort of apples and oranges. You're comparing the rotation of a clump of particles to an actual binary orbit. And we don't necessarily expect this to correspond exactly to binaries, because you could form a triple and eject one, or you could also just lose mass in other ways. But it's sort of the best we can get for now, and it does seem like it's having the same, obviously, general behavior of this broad distribution that strongly favors prograde. And so for reference, this is what a uniform distribution would be. So we're definitely on the prograde side of that uniform distribution. So quickly, I guess I'm almost out of time here. The other binary formation mechanisms you might think about or have heard about, obviously the moon, we think formed by a giant impact, also Pluto-Charon. This simply explains the different class of moons. This is for moons that are very close and tend to have unequal mass ratios. And that doesn't work for things that are separated too far. There's just too much angular momentum. So then there's two different capture mechanisms. The sort of three-body, sometimes called L3, because there's three large bodies interacting, and then one of them takes away the extra energy. Things you have to have sort of fairly high velocity dispersion to get the encounter rate to be high enough. It's probably still not high enough. And this has the this has sort of the opposite prediction, that there's this preference for retrograde orbits. But there's also this serious problem of how would you get the colors to match if things are coming in at sort of high velocities from different regions. So that this mechanism is not favored at all. What is a bit more plausible in terms of the rates, at least, is the so-called L2S mechanism, where you just have two large bodies where the extra energy is taken away not by a third body, but rather by dynamical friction with lots and lots of small bodies. And here you have sort of it's the opposite requirement. You have to have these things encountering each other very slowly so that dynamical friction has time to act on them as they go by. And so then maybe you can think the colors might match if you're just forming from things that form nearby. But that's still not clear, because the rates are still slow, and it can take millions of years, so things will move around. But the bigger problem with this that I think we now know is that here there's a strong, it's not just a mild preference for retrograde. Here the velocity dispersion is so low that you're essentially perfectly flat, and you create, in general, flat and retrograde orbits, which is, definitely not what you see. And even randomizing retrograde, it's hard to see how you get a preference for prograde.
So is the reason that retrograde are preferred is because the inner body is going to be moving with the outer, and when they capture, they're spinning opposite with respect to the direction that they're spinning initially after friction circulates everything?
I'm not sure if there's a simple way to, I mean, it's based on the dynamics of what happens as you enter the Hill sphere on a cold orbit. I guess Hanno's gone. I don't know if he could explain it better. Anyone else? But yeah, except it's not like it's like 60-40. It's you really get retrograde. Yeah. So it's and I don't have the exact numbers, but it's a very strong preference. So we don't, even though this is a mechanism that could work in terms of the rates, it doesn't seem to work in terms of the orientation. So when people are going, that's good because I'm done. So take-home message, how do planetesimals form? They form as binaries. That's the simple answer. Going beyond that, it gets obviously more uncertain, but I think there's growing observational support, a bit from the disks, but especially from the Kuiper belt objects that you form by this gravitational collapse of a sort of pebble cloud, and that the streaming instability is, certainly one way, and one of the more viable small-scale ways of seeding these dense pebble clumps to do this. So thanks.
So are there any questions? Right, so I have a question. So on that plot you had, after you plotted the orientations of the streaming's angular momentum with respect to the background disk. So do you have an idea why you get such a big spread in angular momentum of the streams?
Of the clumps. Yeah, so I mean, I guess there's two parts. So there's one is like, okay, why is there the preference for prograde? And we think that's okay. That's just the sense of disk rotation. So that's where that's coming from. And the randomness is that, well, like we know that if you remember that initial movie, the streaming instability has this tendency of of driving strong vertical motions. So there's, and even though this is the unstratified case, you see that, and I don't have one of these side-on views of the stratified simulations. The midplane, well, sort of see it. The midplane layer is not flat. It creates like it creates these undulations, right? Even in the stratified case, so there's a way to drive it away. Basically, there's a way to drive it away from being perfectly retrograde. And then one of the things in it is that even though there's these undulations, the densest clumps, maybe not surprisingly, tend to be closer to the midplane, and so we're seeing some of this mass effect that you're closer to 0 degrees prograde, somewhat for the more massive objects. Yeah.
So beyond the inclinations to try to tell which one is right, stream instabilities or these captures, two flavors.
Yeah.
Can you think about something else, like branching ratios between binaries and triples? There are triples.
Not many. I mean, I'm trying to think if I know of one or two, but yeah.
I've seen one in one time. So.
Yeah. So I don't. No, I mean, obviously like I was saying, even whether these predictions are viable at all, obviously if you're primarily forming many more, higher end systems, then the initial angular momentum doesn't matter because you lose a lot. It's sort of, yeah, I guess right. Sort of like maybe it was a high-end system and most of them accreted. There's sort of this blobby feature to Mu69 that is sort of, on the one hand, it's like, oh, it'd maybe support gravitational collapse more if these were perfect, perfect spheroids. But obviously, things get messy. But yeah, so it's hard. So I mean, you've got, yeah.
I guess like the widest ones are preferred by dynamic capture. So you have the size of the orbit for a large sample.
Well, I don't know. I mean, the angular momentum is, right. We're getting rotation rates that are, up to sort of what you'd expect from sort of Hill stability. So yeah, no, I would say we can explain the wide ones, and in many, it's actually the opposite. It's that the wide ones are so weakly bound that if you've got some, right. Basically, they're so easy to unbind, so that if you're imagining that it's in this sort of collisional environment with all these small bodies, they would actually unbind the binary, potentially. So there's, so there's so it's been used the opposite way, that the wide binaries are sort of support for sort of gravity as a,
I have a question.
yeah.
So how does the streaming instability, what's the outcome for its effect on, binary formation in the inner solar system versus the Kuiper belt? Like, do you expect it to be more efficient in one place than another?
I can't think of any reason for it to be different. I mean, that's why I was sort of saying, I really just think this should be universal. I mean, it is. There's all the conditions for it to happen. You have to meet the density threshold, and the size, and the sizes that you need to reach are different, right? That having these sort of the aerodynamic properties, so that your stopping time is big enough. In the outer disk, that maybe means you need to grow to millimeters in size, and the inner disk might mean you need to grow to a few centimeters or more in size. But then if you can actually generate the strong clumping, the idea that there would be a difference in the, in whether that clump fragments into multiple objects, I don't see, the only thing I can think of is, obviously binary is not the only, you should have excess angular momentum. Is there another way to get rid of the angular momentum? Is there some reason why you would just form an accretion disk that gets rid of most of the objects versus forming multiples? So these are, no one's really, asked or answered these questions in great detail yet. Oh, Peter has one more? Founder of CITA?
Maybe they're all related questions. You talk about pebbles, but what's that thing made of? What do the colors of the different ones that are binaries say about what they're made of? And what does the fact that it's stuck together tell you about what they're made of?
Oh, yeah. Okay. Yeah. Now when you say what they're made of, you mean like, are they rocks or ices, and is there methane or,
Well, rocks and ices would be a good answer to start with.
Yeah, sure. Yes. Pebble has sort of caught on as a very trendy phrase of, the sort of these small building blocks, and often people use pebble even when they maybe mean something that's more like a boulder in size, but pebble is meant to indicate not a small dust grain, but potentially being rocky or icy. The colors in these objects are interpreted in different ways. There can be methane ice, and then it's right, because there's definitely color variation, and some of that color variation is thought to be due to basically exposure to solar, radiation and, solar wind and other particles, just causing degradation or whatever you call. So there could be some sort of age effect there, possibly, happening early on, perhaps when the sun was more active, and then being frozen in, because obviously everything was formed, 4 billion years ago. But so you have to appeal to, higher radiation environments early on. But
Are these things big enough to differentiate it when there was 126 decay?
I think they're probably too icy, because the first thing the aluminum-26 has to do is melt all your ice and evaporate it away. And then especially in a small object where you're not capturing as much accretional heat, right? You don't have that sort of head start you need. So it's certainly, I think it's, I'd say that there's possibly a definite no to that, but, but it's at least, less likely. Okay, we can discuss more with anyone,
All right. Thank you again, Andrew.